Okay, what is going on, guys? What is up? Today, or this is the first video of a series of videos I'm going to do to review for the midterm. All right, this one's going to be over scientific notation and design of experiments. This is converting numbers into easier to read formats. Design of experiments, that's like IV, DV, control group, and constant. All right, so let's start with scientific notation. So scientific notation, regular numbers are called just standard notation. So if we're going from standard notation to scientific notation, let's break down the rules of what we need to do. This is the general form for scientific notation. This number n is a number between 1 and 10. How do you get n? You need to place the decimal to the right of the first non-zero number. What do I mean by that? Let's look at this example. So let's say we have 54,000. Let me write it. 54,000. You go left to right. What's the first number that's not a zero? 5, which means you put the decimal right there. Put the decimal to the right of the first non-zero number. This means that our n is going to be 5.4. That's going to be our n right here for this example. So you have your n, the big N, then you're going to multiply it by 10 to some exponent power. How do we get this little n? N is the exponent. This is the number of spaces you move the decimal. What do I mean by that? Well, let's go back to this example. Originally, it was 54,000, right? 54,000, the decimal was right here. They didn't write it, but you know that with a number bigger than 1, that the decimal is always at the end. So how many spaces do we move from here to here? Let's count. 1, 2, 3, 4. So this exponent is then going to be 4. Okay? So if you put it all together, wrap it back up, to make this notation, you're going to have 5.4 times 10 to the 4. Now notice I put a positive 4, not a negative 4. Let's explain why. It's not about the direction I move the decimal, it's about the original number. So, if the original number is bigger than 1, that means positive exponent. And then if it's less than 1, original is less than 1, it means negative exponent. Alright? So, the original number was 54,000. That's why we put a positive 4. Let's look at an example that's less than 1. So let's try 0.1268. Let's try that. This is standard notation. We want to put it into scientific notation. So what we do is we need to place the decimal past the first non-zero number. 0, 0, 0, 0, 0, 0, 6. That's the first number that's not 0. Put the decimal right there. Okay? How many spaces do we move from here to here? 1, 2, 3, 4, 5, 6. So we take this number, 6.8, times 10 to negative 6. Why is it negative 6? The original number is a decimal. That's less than 1. That's less than 1. So, if you see a 0 point anything, that's going to be a negative exponent. Okay, now let's go the other way. Let's take scientific notation and go back to standard notation. Let's do that real quick. Scientific. My bad. Scientific notation back to standard notation. Scientific notation back to standard notation. Basically what you need to do is move the decimal according to the exponent. Move the decimal according to the exponent. Negative exponent, move to the left. Positive exponent, move to the right. Alright? So here, the direction does matter. Or the sign does matter for direction. It's the only time it matters. Let's look at some examples. 6.79 times 10 to the 4. Okay? We have a positive 4. Positive means you move to the right. So we're going to move 4 spaces to the right. I'm going to take this and rewrite it here, just so that it's easier to see how I'm moving the decimal. Take this, we go 1, 2, 3, 4. This is where the decimal is now. These 2 spaces, what we need to do is fill in zeros. So 0, 0. So if I rewrite this, it's going to be 679, 0, 0. Double check your work. 1, 2, 3, 4. Looks good. We did it right. Okay, so always double check your work. Double check. Always double check. Okay, so that's a positive exponent. Let's look at a negative exponent. 4.68 times 10 to the negative 3. Just like before, I'm going to write this down here. 4.68, just so you can see it better. We go, negative exponent means I'm going to move to the left. We have a 3, so we're going to move the decimal 3 spaces that way. 1, 2, and 3. Now with these, be careful, wherever you land, that is the decimal now. Same thing as before, these spaces, fill in zeros. 0, 0. So if we rewrite this, it's going to be 0.00468. I prefer to see a 0 in the front, so that way I know it's a decimal clearly. Okay, so this one, just to reiterate, you move the decimal according to the exponent, negative move to the left, positive move to the right. Fill in zeros where you need to, and double check your work. Okay, so that's it for scientific notation. Now let's go to design of experiments. Design of experiments. So, for design of experiments, there's a little trick that kind of helps out. So, design of experiments. We have independent variable, dependent variable, control group, and constants. This, and this. Independent variable, this affects dependent variable. This one is affected by or depends on independent variable. Independent variable. This one's usually measured or recorded. Alright, so that's IV and DV so far. This is abbreviated IV, DV, independent variable, dependent variable. Oops. Usually they say this one's measured or recorded. You might see that in the problem, you might not. But regardless, this is the one that's affected by or depends on this one to change. Control group, this is a group that does not receive the treatment the IV gets. Does not receive the treatment. So usually it doesn't get it at all, or it gets like a different version. Sometimes it's more obvious than other times, but we'll look at some examples. Constants, these are things besides the IV and DV that are kept constant. So the IV and DV change, but everything else needs to be constant. So things besides things beside IV and that remain constant. So it cannot be the IV or DV, just everything else. So let's look at an example. So we're going to look at number 2. Alright, you want to see which type of fertilizer helps plants grow fastest. Oh yeah, before I do this, to get IV and DV. Alright, let's see. To figure out IV and DV. IV and DV. You need to ask yourself 2 questions. Right. So first of all, there's 2 questions you want to ask yourself. First of all, what are they looking for or trying to find? What are they looking for or trying to find? That's the first thing you want to ask yourself after you read the problem. Next question, ask yourself, what affects what? What is affecting what? After you know what they're looking for, ask yourself, what are they trying to see affects what? The first one is the IV, second one is the DV. Okay? So let's look back at this example. So you want to see which type of fertilizer helps plants grow the fastest. So you add a different brand of fertilizer to each plant to see how tall they will grow. You also give no fertilizer to one plant. Okay, so what are they looking for? What are they trying to find? Here it says they want to see how tall the plants grow, right? And which fertilizer helps the plants grow the fastest. So that's what they're looking for. They're trying to see which plant grows the fastest and tallest. Okay? So first question, let's see number 2. They're trying to find out, what are they looking for? They're trying to see which fertilizer plants grow fastest and tallest. Right? So then we have to ask ourselves, what affects what? What affects what? First question, second question. What affects what? Well, if you look back, it says you want to see which type of fertilizer helps the plants grow the fastest, right? So they're trying to see if fertilizer affects, we'll just say plant growth. This is the IV, this is the DV. Trying to see if fertilizer affects plant growth. It has to make sense in this format. What affects what? If it doesn't make sense, you might have flipped them. Sometimes people flip them the wrong way. So, this is type of fertilizer. Type of, this is plant growth. Okay? Type of fertilizer affects plant growth. CON is constant. What are some things you want to keep constant? Just literally anything besides this you want to keep constant. So you can't say type of fertilizer, you can't say plant growth, but you can say anything else. You could say maybe the amount of water, maybe the amount of sunlight, the soil, and I'm just going to put etc. because you can think of a lot of other things. These are just a couple examples. These are good though. Control group. Now remember, control group is a group that doesn't get the treatment that the IV gets, or it's just completely different. So if you notice the last sentence, you also give no fertilizer to one plant. So you're testing different fertilizers on plants, right? If you're giving no fertilizer to one plant, that would be the control group. So we'll say no fertilizer. Okay, so just to reiterate, independent affects the dependent variable. Dependent depends on the independent variable. It's usually the one that's recorded or measured, like plant height or plant growth. Control group, a group that does not receive the treatment that the IV gets. And then the constants is just everything besides the IV/DV has to remain constant.